Okay, so welcome back to another video. So right now, let's try to apply the equations that we've derived and the principles that we've generated from the last video to a simple problem solving. Okay, so step 1, always, when we are dealing with problem solving, we need to write first the parameters or the given that is handed out to us in the problem. So we have a specific gas constant. So the specific gas constant is denoted by R, which is 58.8 foot-pound force per pound mass Rankine. And then we are given the specific heat ratio, which is K, 1.26. Then if 20 BTU are added, so take note that 20 BTU that is added corresponds to your heat. Okay, 20 BTU added to a 5-pound mass. So we have mass which is 5 pounds, 5-pound mass added to this at a constant volume. So lagay natin agad yung assumption, which is V is equal to C when the initial temperature is 90 degrees Fahrenheit. So if you convert that in terms of Rankine, so that is 550. So that is 550 degrees Rankine. Okay? So now, in step 1, we are asked to solve for T sub 2. Okay? So step 1, first assessment. Let's use the combined gas law. This is your first assessment, ha? So P2, V2, T2. So we know that this is a constant volume, so therefore we can cancel out volume. Okay? Next. So if we perform separation of variables, we will have P2 over P1 is equal to T sub 2 over T sub 1. Okay? So as you can see here, we are not given pressure and we are only given T sub 1. Okay? So therefore, we cannot use the combined gas law. Okay? So what do you think is the equation that we can use in deriving T sub 2? Okay? So, very good. We can use the equation of heat. Okay? So we've said that heat is equal to, during constant volume process, is equal to delta U. Okay? Wherein delta U is given by mCV dt or delta T. Okay? So if we expand this one, so we solve this in terms of Q. This is mCV delta T. Okay? So we have mass, we have heat, but we don't have CV. So let's try to solve for CV. So since we are given R, or the specific gas constant, and we are given the specific heat ratio, definitely we can solve for CV by using CV is equal to R over K minus 1. Wherein R is given by 58.8 over K, that is 1.26 minus 1. Therefore, CV is equal to, so let's use our calculator. So we have 58.8 divided by 1.26 minus 1. So we have 226.153. 0.153. So this is in foot-pounds per pound Rankine. Okay? So now we have CV and we have the mass, which is 5-pound mass. So let's try to expand the equation. It's Q, that is mCV T sub 2 minus T sub 1. Okay? So if we expand this one, we are trying to solve for T sub 2. We are going to divide both sides by mCV. So mCV here will cancel out. Then let's try to transpose T sub 1. So therefore we have T sub 2 is equal to Q over mCV plus T sub 1, wherein Q is given by 20 BTU over M, that is 5 pound mass, times CV, that is 226.153. So foot-pounds per pound mass Rankine, plus your T sub 1, which is 550 Rankine. So as you can see here, pound mass will cancel out. We cannot cancel BTU and foot-pounds. So we need a conversion factor. That is, in 1 BTU, there is 778.16 foot-pounds. Okay? So BTU, foot-pounds, leaving us with Rankine. So what will be the value of T sub 2? This will be 20 times 778.16 divided by 5 times 226.153 plus 550 equals, so we have value of 563 point, so let's get 3 decimal places, 763. So 763 Rankine. Okay, so we already solved for T sub 2. Okay, next we are asked to solve for the change in enthalpy. Okay, so how are we going to solve for the change in enthalpy? So that is letter B. So we need to solve for the change in enthalpy. As I've said before, this is absolute, wherein CP dT. Okay, but we don't have the value yet of CP, so therefore we need to solve that. So you can use either CP is equal to CV plus R, or CP is equal to KR over K minus 1. So since I have CV here and I have R here, so ito na lang gamitin natin. So si CP plus, so CV is given by 226.153 foot-pounds per pound mass Rankine, plus R, which is 58.8 foot-pounds per pound mass Rankine. Okay, so foot-pounds per pound mass Rankine plus foot-pounds per pound mass Rankine, therefore we can add them. We have CP is equal to, so 226.153 plus 58.8, so that is 284.953. So foot-pounds per pound mass Rankine. Okay, now we are now ready to substitute it in the general equation of enthalpy, that is delta H is equal to the mass, which is 5 pound mass, times CP, which is 284.953 foot-pounds per pound mass Rankine, times T sub 2, which is 563.763, minus T sub 1, 550 Rankine. So Rankine, pound mass cancel out, leaving us with foot-pounds. However, once we've solved already for this linear function or this linear equation, we need to convert that in terms of BTU. So we have 5 pound mass. So 5 pound mass times 284.953 times 563.763 minus 550, that is 19,609 So that is in terms of foot-pounds. So let's divide it by 778.16. Therefore, we have 25.199 BTU for our change in enthalpy. Okay. So next, what is the next parameter that is being asked? We are asked to solve for the change in internal energy. So that is letter C. So the change in internal energy is given by mCv dt. However, we've said earlier as well that delta U is equal to Q. So therefore, Q here is what? 20 BTU. So we can conclude that the change in internal energy is equal to 20 BTU. Okay. Next is we are asked to locate for the change in entropy. Okay. So the change in entropy, that is letter D, is given by delta S is equal to integral of dq over t from point 1 to point 2. Okay. So let's try to evaluate this one. This is mCv dt over t. So mCv is constant, therefore we will neglect them outside the integral sign. We will have mCv integral of dt over t from point 1 to point 2. Okay, so therefore the change in entropy is equal to mCv ln T2 over T1. So mass is 5 pound mass times CV. So our CV before is 226.153. 0.153, that is in foot-pounds per pound mass Rankine. Natural logarithm of T sub 2, that is 563 if I'm not mistaken. 563.763. 0.763 Rankine over 550 Rankine. So Rankine cancel out, pound mass cancel out. So as you can see, it is in foot-pounds per Rankine. This is 5 times 226.153 multiplied by the natural logarithm of 563.763 divided by 550 equals, so this is 27.974. However, it is in terms of foot-pounds, so therefore we need to divide this one by 778.16. So the change in entropy is 0.0359. 0.0359 BTU per Rankine. Okay. So next, the next thing or the next parameter that is being asked to us is the non-flow work, the work during non-flow process. So letter E, the work during the non-flow process is simply integral of PdV. But we've said earlier that since the volume is constant, this term is equal to 0. So 0 times the function P, regardless of how high the magnitude of P is, your non-flow work is equal to 0. Okay? So, piece of cake. So therefore, we can solve already the required parameters. Okay? So, let's proceed immediately with the next problem. Okay. So, for our next problem, problem number 2, a reversible non-constant volume process decreases the internal energy by 316.5 kilojoules. So, let's write down first our given. So, we have the internal energy, it is said to be decreased. So, therefore, it is negative 316.5. So, kilojoule, that is times 10 to the third joules. And the mass which is 2.268 kilograms, and a specific gas constant R, that is 430 joules per kilogram Kelvin, and we have the specific heat ratio K, which is given by 1.35. So we are asked to locate for the following: what is the work, what is the heat, and what is the change in entropy, assuming that the initial temperature is 204.4 degrees Celsius, or we need to convert that in terms of Rankine, so that is 204.4 plus 273.15 equals 477.55 Kelvin. Okay, so determine the work. So this one is very basic, right? So it is said a non-flow constant volume process. So therefore, the work that is being pertained here is the non-flow work. Okay, so the non-flow work, as we've mentioned before, is P dV. So we know that the non-flow work for this process is equal to 0. Okay, next we are asked to locate the heat. Okay, so how are we going to measure the heat in this one? So heat, we know heat is equal to delta U in a constant volume process. So therefore, heat is equal to negative 316.5 times 10 to the third joules, or negative 316 kilojoule. Okay, next we are asked now to solve for the change in entropy, letter C. So for letter C, it is the integral of dq over t. So this is from point 1 to point 2. Okay, so we know that dq is equal to what? So mcv dt over t. So if we simplify this integral, we have the change in entropy is equal to mcv natural logarithm of t2 over t sub 1. However, as you can notice, we only have one value of temperature. Okay, so we need to solve for t sub 2. How are we going to solve for t sub 2? So very good. We can manipulate your change in internal energy. Because, so sulat natin dito. So let's separate this one. Okay, so we know that the change in internal energy is equal to mcv dt, or t2 minus t1. Okay, so we need to solve for t sub 2 by dividing both sides by mcv. So therefore, t sub 2 is equal to delta u over mcv plus t sub 1. Okay, however, we don't have yet the value of cv, but we are given the specific heat ratio and the specific gas constant. So therefore, cv is equal to r over k minus 1. So R is 430 joules per kilogram Kelvin, divided by K, that is 1.35 minus 1. So CV is equal to, that is 430 divided by 1.35 minus 1. That is equal to 1,228.57. 228.57 joules per kilogram Kelvin. Okay, so now we are ready to solve for T sub 2. Okay? So, T sub 2 is equal to delta U, that is negative 316.5 times 10 to the third joule over M corresponds to 2.268 kilograms times CV, that is 1228.57 joules per kilogram Kelvin, plus T sub 1, that is 477.55. So as you can see, joule cancel out, kilogram cancel out, leaving us with T sub 2, that is Kelvin. So therefore, T sub 2 is equal to, so we have negative 316 kilojoules divided by 2.268 times 1228.57 plus 477.55 equals, so this is 364.141 Kelvin. Okay, so now we have T sub 2. We can substitute for the change in entropy. So that is delta S is equal to M, that is 2.268 kilograms times CV, that is 1208.57 joules per kilogram Kelvin, times natural logarithm of T sub 2, that is 364.141 Kelvin, over 477.55 Kelvin. So cancel, 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 cancel. So we have change in entropy is, so this is 2.268 times 1228.57 natural logarithm of 364.141 over 477.55. So we have, so this is negative 755. So we have negative 755.469 joules per Kelvin. So we can rewrite this one as negative 0.755. So if you want to see that, just press ENG. However, it translates to other parameters. So let's just stick na lang with 755. So joules per kilogram Kelvin. Okay? So I hope you understand on how we solve for the non-flow process or the isometric process dealing with constant volume. So for next video, we'll proceed with constant pressure process or the isobaric process.